Hey guys, Mr. Hallman here with our first lesson on polynomial functions. I know last week we said we were moving into polynomial functions, but it wasn't really a new lesson as it was more a review of synthetic division. And today what we're going to do is we're actually going to put that into use. So hopefully the review last week wasn't too bad and you remembered most of it from what we talked about earlier in the year. So to get introduced to polynomial functions, the biggest difference between solving an equation that involves a polynomial function versus everything else that we've talked about so far is that the process requires us to do a little more work in order to find the solution. In the other processes or other types of equations, we basically follow a step-by-step procedure, and that helps us get to our answer. When it comes to polynomial functions, by definition, that simply means that it's something with an equation that involves variables and numbers. And it can be something like a linear function, could be a quadratic, but in this case, we're really talking about things larger than quadratic equations. So we're looking at functions that involve cubics or quartics or even quintics. So what we're going to do today is we're going to go through our first lesson, which talks about two things, the remainder and the factor theorems. And you're going to want to write these notes out and kind of follow along. And then we'll see in the upcoming weeks how this all goes together with solving polynomial functions. So let's start first today with our factor theorem. So the factor theorem you can see here. Basically what it tells us is that x minus r, this linear binomial, is the factor of a polynomial expression that defines the function p if and only if r is a solution of p of x equals 0. And when we say that, that really means that p of r equals 0. So what we're saying is that a linear binomial is going to be a factor of a polynomial if, when I take the constant term and I plug it into the actual function, I end up with 0. So you can see our example here. It says x minus 2 is a factor of x squared minus 6x plus 8 because when we take the 2 and we substitute it into the function, we end up with 0. And we can just check that real quick. The 2 squared becomes 4. Minus 6 times 2 is minus 12 plus 8. Well, 4 minus 12 is negative 8 plus 8 equals 0. That shows us that indeed x minus 2 is going to be a factor of the polynomial. So let's take a look at two examples where we're going to be using the factor theorem to determine is a binomial a factor of a polynomial or not. Alright, so we're going to test here the factor theorem by using the process of substitution. In other words, we're going to take whatever our linear binomial is, we're going to take the constant and we're going to substitute it into the function. And my factor theorem says that if I end up with 0, then it is indeed a factor. The one thing we want to remember is that we're always checking to see if the linear expression, which is x minus r, is going to be a factor. So in this case, when it says x plus 2 here in number 1, I don't actually want to plug in 2 because x plus 2 is actually x minus negative 2. So what we're going to do is we're going to substitute negative 2 into the function. And I'm going to remember to include parentheses. Anytime we substitute, we want to make sure we include those parentheses. And we're just going to check, do we end up with 0? So let's see, negative 2 cubed is negative 8, plus 5 times negative 2 squared is 4, and then plus 6 times negative 2 is negative 12. So we have negative 8 plus 20 minus 12. Well, negative 8 plus 20 is 12, and then minus 12, that gives us 0. So yes, we would say that x plus 2 is indeed a factor because when we took negative 2 and plugged it into the function, we got 0. Go ahead, pause, try number 2 on your own. Alright, so let's take a look. Here it's x minus 5. So we are just going to use 5. We're going to plug 5 in. 5 cubed plus 8 times 5 squared plus 8 times 5 minus 32. So let's see, 5 cubed is 125 plus 8 times 25 plus 40 minus 32. 8 times 25 would be 200. So now we have 125 plus 200 plus 40, but minus 32. This would be, let's see, 325. And actually the 40 minus 32 would be plus 8. That gives me 333. That is not 0. So we would say no in this case. X minus 5 is not a factor of this polynomial x cubed plus 8x squared plus 8x minus 32. That's basically the factor theorem. We take the constant term, we substitute it in. If we get 0, it's a factor. If not, then no, it is not a factor. Let's look at the next theorem that we're going to use to help us solve polynomial functions. All right, so the second theorem that we're going to use to help us solve polynomial functions is what we call the remainder theorem. And the remainder theorem basically says that if a polynomial expression that defines the function of p is divided by this linear binomial x minus a, then the remainder is the number p of a. So this actually ties directly in with what we just saw with the factor theorem, because we saw that when p of a equals 0, that meant that x minus a was a factor. And in this case, we're saying that the remainder, when you divide by x minus a, is equal to p of a. So what this is really doing in conjunction with the factor theorem is telling us that the remainder of 0 is going to be p of a, and that means that x minus a is a factor. Now, here's the thing. If I know that the remainder is the same thing as p of a, that really gives me two different ways of actually being able to determine if a linear binomial is in fact a factor of the polynomial or not. Because by division, we would use, in this case, the method that we talked about before, which was synthetic division. So I could just go through and take x minus a, take that a value, do synthetic division, determine if it's a factor. But pairing the remainder theorem with the factor theorem, I actually could also use substitution to help me figure out whether a linear binomial is a factor. So there will be times when we might want to use both of these methods, whether it's synthetic division or if it's substitution. Both of them are ways that allow us to determine, is a binomial a factor of the polynomial? Let's take a look at some examples where we're going to use synthetic division. All right, so let's take a look at two examples where we're going to use synthetic division to help us figure out whether or not a binomial is a factor. In number 3, it says p of x equals x cubed plus 5x squared plus 7x minus 6. And we want to know what p of negative 2 is. Now what that means is I could substitute in negative 2, and I would see if I end up with 0, and if I do, then it's a factor. If I don't, it is not a factor. But the important thing to remember here is that p of negative 2 really corresponds to the binomial x plus 2, because when we have x plus 2, that's the same as minus negative 2. So what we're going to do here is we're going to use synthetic division. We're going to use negative 2 as our a value, and we're going to set up our synthetic division. We're going to have our coefficients 1, 5, 7, negative 6, and we're going to go through the process together here. So we're going to bring down the 1, so we get 1. We're going to multiply. Negative 2 times 1 gives me negative 2. Add those together. That's going to give me 3. Negative 2 times 3 gives me negative 6. And then 7 plus negative 6 is 1. Negative 2 times 1 gives me negative 2. Negative 6 and negative 2 adds up to negative 8. So what this means, p of negative 2 equals negative 8. So no, It is not a factor of the binomial. And I could check this. If I were to take -2 and actually plug it into the function, I would also end up with -8 as my answer, indicating that it is not a factor. Go ahead and pause, try number 4 on your own, and then check your answer. All right, so hopefully you did this. Let's check. Here we're checking to see, is x minus 3 a factor? So we're going to plug in 3 for our a value, and we're going to have our coefficients across the top here. So 3, -4, -17, and then 6. And we're going to bring down the 3, and let's go. So 3 times 3 is going to give us 9. And then -4 plus 9 is going to give us 5. 3 times 5 is going to give us 15. -17 plus 15 gives us -2. And then we're going to take the 3 times -2, which is -6. And then the 6 plus -6 gives us 0. So that means that P of 3 equals 0, which means yes, indeed, x minus 3 is a factor. So together, the remainder theorem and the factor theorem, they tell us we can use either synthetic division or substitution to determine whether a binomial happens to be a factor of a larger polynomial function. We're going to use that next week as well, but this week we're basically practicing both of those skills, the substitution and the synthetic division. There's one other thing we're going to talk about this week though, and it has to do with actually working backwards, assuming we already know what the factors are. How can we actually construct a polynomial function? So let's take a look at 2 examples. All right, so what we're going to do here with our last 2 examples is build a polynomial function using some specific information. And you can see here that we're actually going to write our polynomial function in 2 ways, in factored form and then in standard form. And what we're actually going to do is we're going to start with the factored form first. So we'll come up with what that is, and then we'll work our way to the standard form. And the way that we're going to do this is we have some information that's given to us here in the problem, and we're going to set some things up to help us. So the first piece of information that's important is that in this case it tells us the function is of degree 2. That means the largest exponent in the function is going to be 2, which means really that my function p of x, whatever it happens to be, has to be made of 2 binomials. So I know that there's only going to be 2 binomials because I'm going to be changing those into x minus something. The next thing that my problem tells me is that p of 0 equals -3. I'm actually going to hold off on that for a second, and instead I'm going to move to the zeros of 2 and 5. So that's the second step. What that really means is that p of 2 equals 0 and p of 5 equals 0. From our remainder theorem, we know that this occurs, and that means that x minus 2 is a factor, and that if p of 5 is 0, x minus 5 is a factor. So guess what? We just found that our 2 binomials here should be x minus 2 and x minus 5. And this is where we now go back to the middle piece of information here, that p of 0 equals -3. So the third thing tells me if I plug in 0, for the x's, I should end up with -3. So if I check that right now, p of 0, and I take 0 minus 2 times 0 minus 5, that actually gives me -2 times -5, which is 10. I don't want to end up with 10 though. I'm supposed to end up with -3. So the question is, what am I going to multiply this by in order to get -3? Well, I would have to multiply by negative 3 over 10. Because if I took negative 3 over 10 times 10, the 10s would cancel out, and that would simply leave me with the negative 3. So out in front, I'm going to put negative 3 over 10 as a coefficient. This first step here is now my factored form of the polynomial, because I've broken it down into the linear binomials, and I have the coefficient out here of negative 3/10. To get to the standard form, what I'm going to do is I'm basically just going to multiply all this out. So I'm going to leave the negative 3/10. If I FOIL the x minus 2 and the x minus 5, that gives me x squared minus 7x plus 10. And now I'm going to distribute the negative 3/10. So I get negative 3/10 x squared. Negative 3/10 times negative 7x gives me positive 21/10 x. And negative 3/10 times positive 10 gives me negative 3. This would be now my standard form. So here are our two final answers then. In factored form, we have p of x equals negative 3/10 times x minus 2 times x minus 5. In standard form, we have p of x equals negative 3/10 x squared plus 21/10 x minus 3. Let's look at another example. All right, guys, here's another example where we're going to build a polynomial function. Before we start, I do want to apologize for that slight glitch you just saw. What happened was my dog started barking, so to save all of your eardrums from rupturing from her piercing barks, I had to pause the video, which meant that the video cut off, but I could still add on. At any rate, I'm back. Let's go through our last example together. So we want to build, in this case, a function where p is of degree 4. We want p of 0 to equal 6. And we have zeros of 1 with this thing called a multiplicity of 2, a 0 of negative 3, and a 0 of 4. So let's go through the same way we did the last one. First thing that we start with, p is of degree 4. So that tells me p of x is going to be made up of 4 binomials. And you might be saying, well, why are we always breaking it up into binomials? Because when we would factor, we would always want to factor down into linear binomials, in which case we couldn't break anything apart anymore. So that's always going to be our purest factored form if we can get down to these binomials. The second step is now to skip over the p of 0 for a second and look at the last part here. Zeros of 1 with a multiplicity of 2, negative 3, and 4. And in this case, zeros of 1, that means I have x minus 1. But because I have a multiplicity of 2, that means I have this twice. So I'm going to have x minus 1 and x minus 1 again as binomials. I'm also going to have, in this case, x minus negative 3, or in other words, x plus 3. And because we have 4, that's going to be x minus 4. So we're going to fill those in. Now we go back to the middle part here. P of 0 has to equal negative 6. So what we're going to check is if I plug in 0 for these x's, am I going to end up with 6? So let's see. That would give me, if I took p of 0 here, I would have 0 minus 1 times 0 minus 1 times 0 plus 3 times 0 minus 4. So that would give us negative 1 times negative 1 times 3 times negative 4, which actually gives me negative 12. Here's the problem. I want to end up with positive 6. So the question is, what do I need to multiply by in this case to get myself to positive 6? Well, if I took negative 1/2 times negative 12, that would give me positive 6. So the negative 1/2 is going to get thrown out in front here as my coefficient. Here's my factored form. P of x equals -1/2 times x minus 1 times x minus 1 times x plus 3 times x minus 4. And now for the standard form, we're going to work through it. So we're going to leave the -1/2 out here. And maybe you choose to take x minus 1 times x minus 1, make that x squared minus 2x plus 1. And then we can do the x plus 3 times the x minus 4. That becomes x squared minus x minus 12. But then I have to do a whole lot of multiplying here between these two trinomials. So I'm actually going to, again, save the -1/2 out in front. But let's go through here. X squared times x squared is x to the 4th. Then we would have minus x cubed, and we would have minus 12x squared. Then I'm going to distribute the -2x through the second set of parentheses. So that would be -2x cubed plus 2x squared plus 24x. And then distribute the +1. So I'd have plus x squared minus x minus 12. And we're going to combine like terms, and then we'll distribute the -1/2. So if I combine the like terms, I have x to the 4th. I have -x cubed and -2x cubed. So that's going to give me minus 3x cubed. Then I'm going to take -12x squared, positive 2x squared, and positive x squared. That's going to give me -9x squared. And then I'll take positive 24x minus x, and that's going to give me plus 23x, and finally the minus 12. And for our last step, we're going to distribute -1/2. So -1/2 x to the 4th plus 3/2 x cubed plus 9/2 x squared minus 23/2 x, and then plus 6. So there's our p of x, and again, this would be our standard form equation. So our two answers in this case up here in the first step, as well as our last step here for the standard form. Oops, that was not good. Let's try that again. There we go. All right, so there's our final answers. If you wanted to, back up here in the top, instead of writing x minus 1 times x minus 1, yes, you could use an exponent and write x minus 1, the quantity squared. Either one would be fine. So along with using the factor and remainder theorem by doing substitution and synthetic division this week, we're also going to try and construct polynomial functions. Then next week, what we'll be doing is moving on to actually taking a function and trying to solve it using some of the skills that we've talked about this week. We'll have our regular Zoom meeting on Wednesday. I hope that you guys can jump on and join me for it. My guess is this is going to be a little more complicated than some of the things we've talked about so far. So if you have questions, especially with the writing of the functions, please join us. I hope to see you guys. I hope you're all doing well, staying safe, and I miss you guys. Take care and be good.